The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
So we have this wanted information and unwanted information. I call unwanted information noise and wanted information signal. Not all noises are created equal. There are some noises which are partially understood, and I'm claiming this is what we should strip off very quickly, like linear distortions or speaker dependencies. Those are two things I will be talking about. You can easily do it in the feature extraction. There are noises which are expected, but effects may not be well understood. These should go into machine learning part. That's what I'm claiming. This is something which whatever you don't know, you better have the machine to learn. It's always better to use the dumb machine with a lot of training data than putting in something which you don't know for sure. But what you know for sure, it should go here. And then there is an interesting set of the whole noises which you don't know that they even exist. And these are the ones which I'm especially interested because they cause us the biggest problems. Basically, the word you don't know that it exists, noises which somebody introduced which were never talked about, and so on and so on. So I think this is an interesting problem. Hopefully, I will get to it towards the end of the talk, at least a little bit. So some noises with known effects. One is like this. I mean, you have a speech of
you are yo-yo.
And you have another speech which looks very different. But it says the same thing, right? I mean, this is a child, this is an adult. I mean, you can tell this was me, this was my daughter when she was 4, not 30. The problem is that different human beings have different vocal tracts, especially when it comes to children. The vocal tract is much, much shorter, and I was showing you the effect. What happens is that you get a very different set of formants. Like these dark lines, which a number of people believe we should look at if we want to understand what's being said. We have 4 formants here, but we have only 2 formants here. They are in approximately similar positions, but where you had a 4th formant, you have only 2nd formant here. So what we want, we want some techniques which would work more like a human perception, not look at the spectral envelopes, but maybe look at the whole clusters. So this is a technique which has been developed a long time ago, but I still mention it because it's an interesting way of going about the things. So it uses several things. One is that it suppresses the signals at low frequencies. You basically use these equal loudness curves. So you emphasize the parts of the signal which are heard well. Second one is that it uses these critical bands. Because you say, first step which you want to do is to integrate over critical band. This is the simplest way of processing within the band. You integrate what's happening inside. So what you do, you take your Fourier spectrum. This is the spectrum which has equal frequency resolution at all times. There are a lot of details in this case because it's a fundamental frequency. And you integrate over these different frequency bands. They are narrower at low frequencies and getting broader and broader and broader, very much how we learned from the experiment with the simultaneous masking. So this is a textbook knowledge. So you get a different spectrum, which is unequally sampled. So of course you go back into the equal sampling, but you know that there is fewer samples at the high frequencies because you are integrating more spectral energy at high frequencies than in low frequencies. And you multiply these outputs through this equal loudness curve. So from the spectrum, you get something which has a resolution which is more like auditory-like. Then you put it through the equal loudness curve. So because you know the loudness depends on the cubic root of intensity. So you get a modified spectrum. And then you find some approximation to this spectrum, auditory spectrum, saying that I don't think that all these details still have to be important. I would like to have some control, how much spectral detail I want to keep in. So the whole thing looks like this. Start with the spectrum, you go through steps, you end up with the spectrum, which is of course related to the original spectrum, but it's much simpler. So we eliminated information about fundamental frequency, we merged number of formants, and so on and so on. So we follow our philosophy, leave out the stuff which you think may not be important. You don't know how much stuff you should leave out. So if you don't know something and you are an engineer, you run an experiment. You know, research is what I'm doing when I don't know what I'm doing. Supposedly, I don't know, Werner von Braun or somebody was saying that. So we didn't know how much smoothing we should do if we want to derive really speaker-independent representation. So we ran experiment for number of smoothing, number of complex poles telling you how much smoothing you get through autoregressive model. And there was a very distinct peak in the situations where we had a training coming for templates coming from one speaker and a test coming from another speaker. When we use this kind of representation in the speech recognition, I mean to derive the features from the speech, suddenly these two pictures start looking much more similar. Because what this technique is doing is basically interpreting the spectrum in a way the hearing might be doing. It has much lower resolution that normally people would use. It has only 2 peaks, right? But it was good enough for speech recognition. What was more interesting about a little bit of interesting science is we also observed that difference between production of the adults and the children might be just in the length of the pharynx. This is the back part of the vocal tract. That the children may be producing speech in such a way that they are putting already the constriction into right position against the palate. And because they know, or what Mother Nature taught them, that pharynx will grow in a lifetime, but the front part of the vocal tract is going to be similar. So it is a front cavity which is speaker independent, and it is the back cavity, rest of the vocal tract, which may be introducing speaker dependencies. It's quite possible if you ask people how they being trained, like actors, how they are being trained to generate the different voices, they are being trained to modify back part of the vocal. Normally we don't know how to do, but there's some circumstantial evidence for that this might be at least partially true. So what is nice is that, you know, when we synthesize the speech and we made sure that the front cavity is always in the same place, even when the formants were in different positions, we were getting very similar results. So we have this theory. The message is encoded in the shape of the front cavity. Through speaker-dependent vocal tract, you generate a speech spectrum with all the formants. But then there comes the speech perception point, which extracts what is called perceptual second formant. Don't worry about that. Basically, from the at most 2 peaks from the spectrum, and this is being used for decoding of the signal, speaker independently. However, I told you one thing, which is like, don't use the textbook data, and we did exactly. And so I was challenged by my friend, late Professor Fred Jelinek. He is claimed to say airplanes don't flap wings, so why should we be putting the knowledge of the hearing in? Actually, he said something quite different. This is what New York Times quoted after he passed away, because that was supposedly one of his famous quotes. No, he said something else. Well, airplanes do not flap wings, but they have a wings nevertheless. They use some knowledge from the nature in order to get the job done. The flapping of the wings is not important. Having the wings is important if you want to create the machine which is heavier than the air and flies. So we should try to include everything what we know about human perception and production and so on. However, we need to estimate the parameters from the data, because don't trust just the textbooks and that sort of thing. You have to derive in such a way that is relevant to your task. what I wanted to say, you can use the data to derive the similar knowledge, and I want to show it to you. What you can do is to use, again, known from SET, is called linear discriminant analysis. This is the statistician's friend. For this, you need a within-class covariance and between-class covariance matrix. You need the labeled data, and you need to make some assumptions, which turns out are not very critical. But I mean, they are approximately satisfied when you are working with the spectra. So what we did was we would take this spectrogram, and we would generate the spectral vectors from that. So we would always cut part of the spectrum, or short-term spectrum, and we assign it to the label from which part of the speech it came from. So this one would have a label yo, right? And so you get the big box full of vectors. All of them are labeled. So you can do LDA, and you can look what are discriminants are telling you. From LDA, you get the discriminant matrix, and each of the row of the column or row, whatever, creates the basis on which you should project your spectrum, right? These are the 4 lowest ones. Here you also have amount of variability present in this discriminant matrix which you started with. What you observe, which is very interesting, is that these bases tend to project the spectrum at the beginning with the more detail than the spectrum at the end. So essentially, they appear in the first look, they appear to be like emulating properties of human hearing, some of the well-known properties of human hearing, namely non-equal spectral resolution being verified in n ways, many, many ways. Like among them was one I was showing you this masking experiment of Harvey Fletcher. There's a number of reasons to believe that this is a good thing. This is what you see. So essentially, if you look at the zero crossings of these bases, this is the first base, they are getting broader and broader, so you are integrating more and more spectrum, right? This is all I thought I'll leave it out. This is from another experiment with the larger database, very much a very similar thing. Eigenvalues quickly decay. But what is interesting, you can actually formally ask what is your resolution by doing what is called perturbation analysis. So you take, say, some signal here, this is a Gaussian, and you project it on this LDA basis, then you perturb it, you move it. And you ask how much effect this movement of this, say, emulated spectral element of the speech causes at the output, seen as the output of this projection of this many, on these many bases. And what you see is, as I was suggesting, spectral sensitivity to the movements of the formant is much higher at the beginning of the spectrum and much less at the end of the spectrum. You can actually compare it to what we had initially in the PLP analysis when we integrated the spectrum based on the knowledge coming from the textbook. And it's very much the same. If they were just a plain cosine basis computing Merkel-Kapstrom, sensitivity is the same at all frequencies. But these bases derived from LDA, they're very much doing the thing which critical band analysis would be doing. And so this is you can look at it. It was a PhD thesis from Oregon Graduate Institute by Naren Malayat, who is now big. You better be friends with him. He's at Qualcomm. I think he's the head of image processing department. We better be good friends with him. Scratch it. Okay, another problem is linear distortions. Linear distortions, boy, that was a problem. Now it's not a problem anymore. But in old days, this was a problem. The problem shows up in a rather dramatic way, in the following way. Here we have one sound.
Beat.
Beat. So B, E, T. Here is the very distinct E. Every phonetician would agree this is E. High formant, cluster of higher formants, and so on. Some vicious person, namely one of my graduate students, took this spectral envelope, designed a filter which is exact inverse of that, and put this speech through this inverse filter. So it looked like this. There is a spectrum where there were 9 points. It's entirely flat. And if you listen to it, probably already guess what you will hear.
Beat.
You hear the filtered speech, right? But you
Beat.
It's okay, but this oops, that's what you would. Sorry.
Beat. Beat. Beat.
But whoever doesn't hear E, don't spoil my talk. I mean, I think everybody has to hear E, even though any phonetician would get very upset because he said this is not E. Because of course what is happening, human perception is taking relative percept relative to the neighboring sounds, right? And since we filtered everything with the same filter, I mean relative percept is still the same. So this is something which we needed to put into our machine. And we did. Actually, this is a very straight, signal processing wise, the things are very straightforward. Because what you have, the signal is actually signal of the speech convolved with the spectrum of the impulse response of the environment. So in logarithmic domain, this is a signal processing stuff. Basically, you have a logarithmic spectrum of the signal plus logarithmic spectrum of the environment, which is fixed. So what's happening here is that if you remove somehow this environment, or if you make it invariant to this environment thing, then you may be winning. The problem here is that each frequency you have a different amount of additive constant, because this is a spectrum, right? If it was just a constant of all frequencies, you just subtract it. But in this case, you can use the trick. You remember what Josh told us this morning. Hearing is doing spectral analysis, and what I try to tell you that at each frequency, each critical band, this trajectory of the spectral energy is independent of, in the first approximation, of the others. You can do independent processing at each frequency band, and maybe don't screw up that many things. So this was kind of a step which we took. We said, okay, we will treat each temporal trajectory differently, but we will filter out stuff which is not changing. So separate it to different frequency channel, do the independent processing in each channel. And processing was that we would take first logarithm, and then we would then we put each trajectory through bandpass filter, which would which would be suppressing DC and slowly changing. Namely, it was suppressing anything which was slower than 1 Hertz. And also, it turned out it was useful to suppress things which are higher than about 15 Hertz. So what you get out, this was the original spectrogram. This was the modified spectrogram. Things got a little bit, this trajectory got a little bit smoother. Transitions got because there was a bandpass filter. There was a high-pass element to that. Very much what we thought, well, this is interesting. Maybe that's what a human hearing might be doing. To tell you the truth, we didn't know. It was, for the people who are from MIT and who are working in image, it was inspired by some on a perception of lightness, what David Mark called lightness. And here was the type thing which I told you about, 6 by 749. David Marr was talking about processing in space. We applied it in processing in time, but it was still kind of good enough. I mean, so we definitely got rid of the problem. So here it is. I mean, you know, the spectrograms which look very different suddenly start looking very similar. What good thing was, remember, I'm an engineer. I was working for a telephone company at the time. It was working better in some problems which we had before, and we had a severely mismatched environment. Getting a training data from Bell Labs and testing it in the US West in Colorado. So it didn't work at all. Recognized after this processing, everything was cool and dandy. Okay, so now we have a raster, LDA, and we can do the same trick. How about that? So you take the spectral temporal vectors, and you label each of these vectors by the label which is of the phoneme which is in the center of this trajectory. And just for the sake of, just to have some fun, we took rather long trajectories, about 1 second. And we said, well, what kind of projections would these temporal trajectories would go on if we wanted to get rid of speaker-dependent, I mean, of environment-dependent information. Well, these were the impulse responses, these were the frequency responses. Because in this case, you get FIR filters. These discriminants are FIR filters, which are to be applied to temporal trajectories of spectral energies. Because it's just basically projection of the spectrum on the and basis is 1 second long. This is impulse response. Cannot be all that long because eventually they become 0, right? If it is not, if you should do nothing to it, you do nothing. But you can see active part is about a couple of 100 milliseconds, maybe a little bit more. And these are the bandpass filters. So essentially between the 1 hertz and 10, 15 hertz. Very similar at all frequencies. That was another thing which we were very interested in. Should we do different things at different frequencies? Answer is pretty much no. And so that was very exciting. Well, anyways, let me tell you yet more experiment which just happened and is going to be presented next week. Well, we wanted to move into the 21st century, so we did convolutive neural network. But our convolutive network is maybe not what you are used to, when you have a 2D convolutions there, but we just said we will have a 1D filter as a first processing step in this deep neural network. So we postulated the filter at the input to the neural network, but in this case we trained the whole thing together. So it wasn't just LDA and that sort of thing. And so we forced all filters at all frequencies be the same because we expected that's what we want to get. And we were asking how these filters look like, which come from the convolutive neural network. Well, again, I mean, I wouldn't be showing it if it wasn't at least somehow supportive what I want to say. They don't look all that different for what we were getting from LDA. They definitely are enhancing the important modulation frequencies around 4 hertz, right? They are passing number of them. I'm showing 3 here, which are somehow arbitrary. They are passing, but most of them look like that. I mean, we used 16 of them. Passing in 1 and 10 hertz in modulation spectral domain, so changes which are 1 to 10 times a second. It's coming out in the paper, so you can look it up if you want. Last thing, which I still wanted to do, I said, well, you know, maybe it has something to do with the hearing after all. We were deriving everything from speech. There was no knowledge about hearing, except that we said, we think that we should be looking at long segments of the signal, and we expect that this filtering will be very much the same at all frequencies. Actually, not even LDA will come out automatically. There wasn't much of the knowledge from human hearing going on. In the first one, when I was showing you critical band spectral resolution, we started with Fourier spectrum. We did not tell anything about human hearing. And what comes out is the property of human hearing. I mean, tell me if there is yet another strong evidence that speech in such a way that it fits human hearing. Because the only thing which was used here was the speech labeled into classes which we are using for recognizing it, speech sounds. So what we did was, that was with Nima, with Garani, and my we took number of these cortical receptive fields, which we talked about it before a little bit, about 2,000-3,000, whatever. We basically swept the floor at the University of Maryland and computed principal components from these fields in both spectral and temporal domain. But here I'm showing the temporal domain. How they look very much like the Rasta filter. This is what is happening. It's a bandpass. Peak is somewhere around 4 hertz. Essentially, I'm showing you here what I understand might be a transfer function of your auditory cortex, derived with all the usual disclaimers, like this is a linear approximation to the receptive fields, and they might have been problems with collecting it, and so on and so on. But this is what we are getting as a transfer function of auditory cortex. I'm doing fine with the time, right? So you can do experiment in this way. You can actually generate a speech which has certain rates of change eliminated by doing this, computing the capstone, do the filtering of each trajectory, and reconstruct the speech, and ask people what do they hear, how do they recognize speech. You can also ask your recognizer. For this, you don't have to regenerate the speech, but you just use the LPC capstone. This is the full experiment with, this is what is called the residual excited LPC vocoder, but it's modified in such a way that you artificially slow down or modify the temporal trajectories which are being used. If there is no filter, you get a replica of the original signal here at the output. And so just the bottom line of the experiment here is, if you start removing components which are somewhere between 1 and 16 hertz, you are getting hurt significantly. Most you are getting hurt in perception when you are removing component between 2 and 4 hertz. That's you are getting biggest hit. Here we are showing how much these bands contribute to recognition performance by humans. This is a white bars, and to speech recognizer. Those are the black bars. So you can see that in speech recognition, machine recognition, you can safely remove stuff between 0 and 1 hertz. It's not going to hurt you, it only helps you in this task. In speech perception, there is a little bit of hit, but certainly not as much hit as you are getting when you are moving to the part where you hear the. And certainly the components higher than 16 or 20 hertz are not important. That already Homer Dudley knew in 1930 when he was designing his vocoder. But it was a nice experiment. It came out in JASA, so you can look it up a long time ago. Just to summarize what I told you so far, Homer Dudley was telling us information about the message is in a slow modulation, slow movements of the vocal tract, so which modulates the carrier. Information about the message is in slow modulations of the signal, slow changes of speech signal in individual frequency bands. Slow modulations imply long impulse responses, right? So 5 hertz by something around 200 milliseconds. My magic number of critical interval, which we have observed in this summation of subthreshold signals and temporal masking and so on. I have here a number of things which I listed. Frequency discrimination improved. If you are longer than 200 milliseconds, below 200 milliseconds of signal, you don't get such a good frequency discrimination. Loudness increases up to 200 milliseconds, then it stays constant, depends on the amplitude. Effect of forward masking I was showing you lasts about 200 milliseconds, independent of the amplitude of the masker. And subthreshold integration was also showing you. So I'm suggesting there seems to be some temporal buffer in human hearing on some level. I suspect it's cortical level, which is processing. Whatever happens within this buffer is fair thing to treat as a one element. So you can do filtering on it, you can integrate it, and basically all kinds of things. If things are happening outside this buffer, this part should be treated as a part. So how does it help us? You remember the story about the phonemes. You remember that phonemes don't look like this, but they look like this. Length of the co-articulation pattern is about 200 milliseconds, perhaps more. So what is a good thing about it is that if you look at sufficiently long segment of the signal, you will get whole co-articulation pattern in. And then you have a chance that your classifier is getting all the information about the speech sound for classifying this sound. And then you may have a chance to get a good estimates of the speech sounds. but you need to use these long temporal segments. And here I can say it even to YouTube. I think we should claim the full victory here, because most of the systems do it nowadays. They use the long segments of the signal as the first step of the processing. So I can happily retire telling my grandchildren, well, we knew it. Actually, we weren't the only ones, but I mean, we were certainly using it for a long time and promoting it for a long time. In such a way that we even design several techniques which do that. So this is a classifying speech recognition from the temporal patterns directly. So we would take these long segments of the speech, do some pre-processing, put neural net on every temporal trajectory, trying to estimate the sound at each frequency, each carrier frequency, and then we would fuse all these decisions from different frequency bands, and then we would use the final vector of posterior probabilities. Unlike what people do most often, that they just take the short-term spectra, and then they maybe now take the longer segment of this block of these short-term spectra. We say short-term spectrum is good for nothing. We just cut it into pieces, and we classify each temporal trajectory individually in the first step. Turned out that it may be useful later when I be telling you about dealing with some kind of noises. But you understand what we did here, right? Instead of using the spectral-temporal blocks, we would be using temporal trajectories at each critical band, very much along the lines what we think that hearing is doing with the speech signal. First thing is hearing is doing, takes the signal, subdivides it into individual frequency bands, and then it treats each temporal trajectory coming from each of these cochlear filters to extract the information, and then tries to figure out what to do with this information later, right? Well, we have another technique called EMRASTA, just for people who are interested in a cochlear, I mean, or cortical modeling. We take this data, we project it on number of projections with variable resolution, so we get a huge vector of the data coming from different parts of the spectrum, and then we feed it into speech recognizers. The filters look like this. I mean, they have a different temporal resolution. Spectral resolution, we are pretty much integrating and differentiating over 3 critical bands, following some of the filters coming from these 3, I mean, old PLP, low order model, and 3-bar critical band integration. So, you know, these ones look a little bit like what people would call Gabor filters. But they are put together basically from these two bases in time and in frequency, different temporal resolution enhancing different components of modulation spectrum. Again, I mean, you may be claiming that this is something which resembles the Thorsten Dow, which Josh was mentioning in the morning, these cochlear filter banks. Auditory, I mixed the cochlea and cortical filter banks, modulation filter banks. So there are some novel aspects in this type of processing I want to stress. There was novel in 1998, but is, as I said, it's fortunately becoming less novel 15 years later. Uses rather long temporal context of the signal as an input. It uses already hierarchical neural nets, so deep neural nets, which wasn't around in 1998. The only thing was that there was independent processing of frequency of neural net estimator at different frequencies. The only thing which we didn't do at the time, and I don't know how important it is, I don't think it does any hurt, it hurts anybody. We were training these parts of this system, this deep neural net, individually, and just concatenated outputs. So we never did training altogether as we do now in convolutive nets and that sort of thing, because simply we didn't even dream about doing that because we didn't have the hardware. That was one thing which I tried to point out during this panel. A lot of progress in neural nets research and success of the neural nets comes from the fact that we have very, very powerful hardware which we didn't have. So we didn't dream about many things doing, even when they might have made sense. So, okay. Where are we? Oh, I see. One more thing. Co-articulation. This is a problem which is known since people start looking at the spectrograms. There's some consonants like a k or h. They are very dependent on what's following. So k in front of e, ki, ku, ka, we have k has a burst here. In front of u has a burst here. And if in front of a, there's a burst here. So the phonemes are very different depending on the environment. When you start using these long temporal segments, and all the tricks, or some of the tricks I showed you about, what comes out are the posteriogram in which the k almost looks the same as the k. It basically recognizes since it looks at the whole co-articulation pattern, all group of the phonemes, in order to recognize this sound, it does the right thing. So I suspect that success of these long temporal contexts, which people are using now in speech recognition, come from the fact that it partially compensates for the problems for the co-articulation. And what I also wanted to say, the co-articulation is not really a problem. It just spreads the information for a long period of the time. If you know how to suck it out, it can be useful. But it's a terrible thing if you start just looking at the individual frequency bands, individual frequencies, slices of the short-term spectrum. So it's another deep net, I mean, sort of deep net from, I don't know, natives. So it was already almost legal deep net. You estimate the posteriogram from the short window in the first step for about phoneme length window, and then you take the long, I mean, the big window of the posterior, train another neural net, you get much better areas which also work better. Again, the mainstream technique nowadays, it's being used in most of the DARPA systems. Oh, yes, one more thing. I want to stress this one. So I'm sorry, I didn't want to show it all at the same time. Anyways, I don't think there's anything which is terribly special about short-term spectrum of speech. I think what really matters is how you process the temporal trajectories of the spectral energies. This is what the human hearing is doing, that seems to be doing a good job on our speech recognizers. So essentially, this is one message which I want to say. Don't be afraid to treat different parts of the spectrum individually. You may get some advantages from that. Started with Rasta, but it shows up over and over again. So away from the short-term spectrum, go away, start using what hearing is doing. Start using the temporal trajectories of the spectral energies coming from your analysis. To the point that we did this work with Marios and then Alice on going directly, don't do this, and don't get your time frequency patterns from the short-term spectra, but think about the ways how to get directly what you want. Turns out that there is a nice way of estimating directly the Hilbert envelopes of the signal in the frequency bands called frequency domain linear prediction. Marios was his PhD thesis, and we were working together for a couple of years. So what you do, instead of using a time trajectory to use this, in this case, autoregressive modeling, LPC modeling, and put the windows on a time to get the frequency vectors, you do it on a cosine transform of the signal. So you move the signal into sort of frequency domain, and then you put the windows on this cosine transform of the signal, and you derive directly the all pole approximations to Hilbert envelopes of the signal in the subbands. You don't ever do the Hilbert transform. You just use your usual techniques from autoregressive modeling. The only difference is on the cosine transform of the signal, and your windowing determines which frequency range you are looking. So of course, what you typically do, you can use the longer windows at higher frequencies, shorter window of lower frequencies, you do all these things. But this is a convenient way. It's convenient, this is more like fun, but maybe somebody might be interested in that. So essentially, what you do, what you do is that you take the signal and you eliminate the modulation component out of that AM component, which is with which the signal is being modulated. So this carries the information about the message, and this is the carrier itself. And you can do what is called a channel vocoder, which we did, and you can listen to the signal. So this is, in some ways, is interesting. Original signal.
They are both trend-following methods.
Oops, try to make it somehow.
They are both trend-following methods.
Somebody may recognize Jim Glass from MIT in that.
In an ideological argument, the participants tend to thump the table.
So this is right. Now you can look. What you get if you just keep the modulations and excite signal with the white noise. Oops, sorry. Oops. What am I doing? Oh, here.
They are both trend-following methods.
Can you recognize Jim Glass? I can.
In an ideological argument, the participants tend to thump the table.
And then you can also listen to what is left after you eliminate the message. Maybe it's a male, right? This is fun. This is fun. It may have some implication for speech recognition, but certainly if I have seen one verification of what old Homer Dudley was telling us, where the message is, I mean, this is it, right? Anyways, what is good for that is that once you get the all-point model, it's relatively easy to compensate for linear distortions, because main effect of linear distortions is basically shifting the energy at different frequency bands by different amounts. But all this information is in the gain of the model. It's one parameter which you essentially after you do this frequency domain linear prediction. And you get a very similar trajectory for both. This is a telephone speech and clean speech, which differed quite a bit. And I hope that I have, this is for reverberant speech. There seems to be also some advantage, because reverberation is in the first animation. It is a convolution with the impulse response of the room. So you make if you use the truly long segments, in this case we use about 10 seconds of the signal approximating by this all-point model and eliminated the DC, from that, you seem to be getting some advantage. So known noise with unknown effects. I say train the machine on that. Here is the one example, right? You have a phoneme error rate, noisy timid. If everything is good, clean trading, clean test, you have about 20% phoneme accuracy. This is kind of state-of-the-art result, reasonable result. But once you start adding a noise, things quickly go south. Typical way of dealing with it is that you train multi-style. So if you know which noises you are going to deal with, you train on them, and things get better. But you pay some price. I mean, certainly you pay the price on clean, because you recognize your model became much mushier, basically. It's not very sharp model. So here we had a wonderful 21%. We pay 10% relative price for getting this better performance on the noises. What we observed is that you get much better results, noticeably better results, if you would have different recognizers for each type of noise. So, but of course, the problem is that you have different types of noise, so you have this number of recognizers, but now you need to pick up the best stream. And how do you do that? This is something, again, which I was mentioning. This is something which we are struggling with, and we don't know how to do that. If you are a human being, maybe you can just look at the output and you can keep switching. after your message starts looking reasonably well. But if you want to do it fully automatically, I don't know why we want to only build a fully automatic recognizers, but that's what we are doing. So you want to pick up you want a system to pick up the best stream. So how do we do that? First thing is, of course, one way is to recognize type of noise. This is a sort of typical system nowadays. You recognize type of the noise, and you use the appropriate recognizers. BBN is doing it. My feeling is that it's somehow cleaner and more elegant to be able to figure out what is the right output, because what matters is not what is the signal, but what is the signal interacting with the classifier. So for this, we have to figure out what the best means. So here we have two posteriograms. If you look at it, if you know that these are trajectories of the posteriors, of the speech sounds, you know this one is good, this one is not so good, because the word is nine, n, I, n, right? Here is a lot of garbage. So I would know that it automatically. So ideally, I would pick up the stream which gives me the lowest error, but I don't know what the lowest error is because I don't know what the correct answer is. That's the problem, right? So one is to maybe try to see what my eye did, try to figure out which posteriogram is the cleanest. Another one is following thinking. Like when I train the neural net on something, it's going to work well on the data on which it was trained. So I have some gold standard output. And then I will try to see how much my output differs if it's the test data which are not the same as the data on which the recognizer was trained. So both of these tricks we were using. So first one uses kind of technique which is like this. You look at the differences between posteriors or KL divergence posteriors a certain distance from each other, and you slice this window, you do cumulatively over as much data as you possibly can. And what you observe is that if you have a good clean data, this cumulative divergence keeps increasing, and after you cross the point where there is a coarticulation pattern or coarticulation ceases, suddenly you start getting pretty much the fixed high KL divergence, cumulative KL divergence. If we have a noisy data, the noise starts dominating these KL divergences, and differences are less, because the signal in the first place carries the information, and information is in the changes. But noise is creating the information which sort of it doesn't have these segments or something. So this is one technique which we use. Another technique which is even more now popular, at least in my lab, train another neural net. We train this autoencoder on the output of the classifier. And we say, so on the output of the classifier, S is being used on its training data. And we say autoencoder then will learn how, in average, the output from the classifier used on its training data looks like. And then we use it on the output from the classifier used to unknown data. And if the autoencoder is a neural net which tries to predict input on its output. This is how it is being trained. So if the output, if the prediction is not very good, then we say we are probably dealing with the data for which the classifier is not good. This is how it works. I mean, you know, it's on this. If you are looking at the output of the neural net, which has been applied to its training data, the training data is matched. Pretty much the error is very similar as it was on the training data. When you apply it to a data for which the classifier wasn't trained, your error is of course much larger. Prediction of the output of the. So there is a double deep net. One is classifying, and then another one is predicting its output. the one which predicts output is trained to predict its best output it can possibly have, which is the output on the training data of the previous classifier. I don't know if you follow me or if it is becoming too complicated. But essentially, we are trying to figure out if anything like it is looking on the training data when applied on the training data. So it seems to be working to some extent. Here we have a multi-style results. Here we have a matched result. This is what we would like to achieve. Of course, this is oracle. This is what it would be ideal if we knew which stream is best. This is what we would be getting. But what we are getting is not that terribly bad. I mean, it certainly is. It is typically better than multi-style training, right? And we have some ways to go to oracle, but not too far from the matched field. Sometimes it's even better because it's making decision on every utterance. So sometimes it can do quite well. So we were capable of picking up the good streams and leaving out the bad streams, even at the output of the classifier. How does it work on previously unseen noise? Fortunately for this example, we still seem to be getting some advantage. We are using noise which has never been seen by the classifiers, but still it was capable of picking up the good classifier, which is actually better than any of these classifiers. Sort of, so this seems to be good. Another technique of dealing with unseen noises is actually the one which I like maybe even a bit more, which is like you do the pre-processing and in sub-processing in sequence, hoping the main effect of different noises is in shape, spectral shape of different noise. So if you are doing recognition in the subbands, then the noise start looking, in each subband starts looking more like a white noise, except of different levels. So meaning like sort of that, you know, here maybe the signal to noise ratio is higher, here it is more miserable. But if I have the classifier which is trained on multiple levels of the white noise in each frequency band, perhaps I can get some advantage. So I do what the cochlea might be doing, which is like I divide each the signal into the number of frequency bands, and then I have a one fusion DNN which will try to put these things together. But each of these nets are going to be trained on multiple levels, but this time of the white noise, and it's going to try to noises which are not white, or the noise which is not white. So how it works, I mean, you can figure out if this was done in the case of Aurora. So here we have the examples here, how it works on in the matched situations. Here is multi-style training. But here it is what you are getting if you apply this technique. This is what you get on multi-style training. But in the subband recognition, you are getting half of the error rate. Just a simple trick, which I sort of think is reasonable, which is like you do this subband recognition. There's a number of parallel recognizers, each of them paying attention to part of the spectrum. And then each of them is being trained to handle the white noise, a simple white noise. But you turn, in some ways, arbitrary additive noise, the car noise, into white-like noise in each subband. And that's what you do. So in general, dealing with unexpected noise is you want to do the adaptation. You want to modify your classifier on the fly. You want to have parts of the classifier or some streams which are doing well, and some of the parts of the classifier are still reliable, and you want to pick up these streams which are reliable on unseen situation. So this is what we call this multi-stream recognition, multi-stream adaptation to unknown. So you assume that not all the streams are going to give you good result, but you assume that at least some of the streams are going to good results, and all these streams are being trained on, say, clean speech or something. And so this is this multiband processing, right? So this is what we do different frequency ranges, and then you use our performance monitor to pick up the best stream. So here is the one experiment which we did. So you would have the 31 processing streams created from all combinations of fine frequency. One stream was looking at full spectrum, and the other streams were only looking at the parts of the spectrum. So more black ones, there is a more spectrum, more white, some of them are looking only at a single frequency band. So we have this number of processing channels, and we would hope if the noise comes here, maybe this one is going to be good because this one is not going to be, not picking up this noise, or recognize basically which only uses the bands which are not noisy, going to be good. So this is the whole system. It was published in 2013, like interspeech. We had the subband recognition, fusion, performance monitor, and then selecting the best stream. This is how it worked. This is again showing for car noise. Car noise is very nice because it mainly corrupts the low frequencies, so all these subband techniques work quite well. But you can see that it's pretty impressive. I mean, sort of, if you didn't do anything, you get 50% error. With this one, you get 38% error. If you knew which bands to pick up, you would be getting Oracle experiment, cheating experiment. You would be getting about 35%. So that was, I thought, quite nice. Just to conclude, so auditory system doesn't only look like this, that it starts with a signal, does the analysis, and then it reduces the bit rate, but it also increases number of views of the signal. And this is based on the fact that there is a massive increase in number of the cortical neurons on the level of the cortex. So there is many ways of describing information at high level of perception. Essentially, the signal doesn't go through one pass, but it goes through many passes, and then we need to have some means, or we have some means to pick up the good ones and ignore the other ones, maybe switch them entirely off. This is sort of like vision. So this is the processing in general, signal. You get the different probability estimates from different streams. And then you need to do some fusion and decide based on the level of the fusion. How you can create the streams. We were showing you differently trained probability estimator on different noises, different aspects of signal, that is different parts of the spectrum of the signal. But you can go wild. You can start thinking about different modalities. I mean, because as we talk about it also at the panel, you know, very often audio-visual modality carries the same information about the same things. Imagine fusion of audio-visual streams. You can also imagine the fusion from streams with different levels of priors, different levels of hallucinations. So basically, this is what I think human beings are doing very often. If the signal is very noisy, you are at a cocktail party, you are guessing, because that's the best way to get through. If the communication is not very important, it's not about your salary increase, but about the weather. So basically guessing what the other people are saying, especially if they speak the way I do, right, with a strong accent or something. So the priors are very important, and streams with priors are very important. We use this to some extent, I was mentioning, by comparing the streams with different priors to discover if the signal is biased in the wrong way by priors. And sort of. So stream formation, there is a number of PhD theses right here, right, I think. Fusion, oh, why? Select the best probability estimates. I tell you, this is the problem which I was actually asking for. Please help me to solve it. Because we still don't know how to do that. I suspect that especially in human communications, people are doing it as it starts making a sense if they use the certain processing strategy. So people can tell if the output of our perceptual system makes sense or not. Our machines don't know how to do it yet. Conclusion. So some problems with the noise are simple. You know, you can deal with it on signal processing level by writing spectrum, filtering the trajectories, because these effects are very predictable, and if you understand them, you should do it. Because there's no need to train on that. You just do it, and things may be working well. Unpredictable effects of noise can be typically are being handled by multi-style training, and these amounts of training are enormous nowadays. You know, if you talk to Google people, they say we are not even interested in this, what you are doing, because we can always collect more data from new environments. But I think I shouldn't say dishonest. I'm sorry, scratch it. It's not the best engineering way of dealing with the things, because I think the good engineering way of dealing with the things is to get away with less training and that sort of thing, and maybe follow what I believe the human beings are doing. So we have a number of parallel experts working with different aspects of the signal, giving us a different pictures, and then we need to pick up the good ways of dealing with it.